Energy, it's the pulse of life. It's what makes the world go round and round. Energy, it joins everything from the sun above to oil underground. Energy can take so many different forms, like pumping muscles, the flash of lightning storms, the beat of a rock band, the sleek thoroughbred. Sometimes it takes a lot of it to get out of bed. It all begins with the sun, and without it we're done. Energy, it's the pulse of life. It's what makes the world go round and round. Round and round. Round and round. Round and round. Energy.
The universe can be reduced to two principles: matter and energy. It's easy to appreciate matter. You can see it, touch it, measure it, weigh it. But energy is harder to grasp. 1 second it is there, and the next it's gone. It keeps changing form and flits from place to place. But it is energy that makes the world and everything in it go round. There is energy in a moving object, in the pull of gravity, in the heat of a fire, in the bonds of a chemical, in an electrical current, in a ray of light, in the nucleus of an atom. We usually think of energy as the ability to do work. Certainly we need energy to do work, but as we will see, not all energy can be put to work. Energy, it seems, is easier to recognize than to define. To understand energy, we need to find common threads in what looks like an ever-changing, crazy quilt of events. One such thread is the continual flow of energy from one form, object, or place into another. In fact, every physical event can be viewed as an energy transaction and measured and compared with any other event using a common set of energy terms and rules. To a scientist, energy is an invaluable tool for investigating the universe around us. Dr. John Polanyi of the University of Toronto won the 1986 Nobel Prize for Chemistry.
Anybody's science really makes use of this concept of energy. It's one of the most dazzling generalizations ever to come the way of scientists, and it knits together things that seem so incredibly disparate.
Our scientific understanding of energy began with the study of motion and gravity. In 1581, the teenage Galileo was sitting in the Cathedral of Pisa, Italy, when the swinging movements of the chandelier caught his eye. Using his pulse as a timer, he noted each swing of the chandelier took the same time, no matter how wide the arc. Galileo later showed that when two objects of different weight but similar air resistance were dropped from the same height, they fell at the same speed and landed at the same time. A century later, Isaac Newton extended Galileo's discoveries about gravity at the Earth's surface to include gravitational forces anywhere in the universe. He then summarized it all in his famous law of universal gravity, which can be used to accurately predict the orbits of satellites around the Earth or planets around the Sun. Although they didn't describe moving objects in terms of their energy, Galileo and Newton had taken the first scientific steps towards understanding energy in its most visible form.
Kinetic, kinetic.
Anything that moves carries with it kinetic energy. The work done in climbing, or lifting something to a higher point against the force of gravity, results in another energy form.
Potential.
Gravity can then convert this energy back into kinetic energy. pendulum shows energy changing back and forth from potential to kinetic. At the top of the arc, its energy is all potential. At the bottom, it's all kinetic. And at all other points along the arc, it's a combination of both. An elastic device like a trampoline can also convert energy back and forth from kinetic to potential.
Heat, heat, heat. Heat, heat, heat.
The heat of a fire was probably man's first use of an energy resource outside of his own muscle power. Whenever something is heated, its molecules move faster, so heat is really a kind of kinetic energy. The hotter a substance becomes, the faster its molecules move.
Electrical, electrical.
Electrical energy is formed when work is done to separate a negatively charged electron from the rest of its atom, which is left positively charged. The potential energy of the displaced electron can then be conducted along a wire towards a distant positive charge as electrical current. Electrical energy is so useful because it is easily transported and converted into other energy forms. A pulsating electrical current sends out electromagnetic waves. These waves exhibit another form of energy.
Radiant.
There is a wide spectrum of radiant energy, all of which travels at the speed of light. At one end of the energy spectrum are low-frequency, low-energy waves, like radio. Then come higher-frequency, higher-energy light waves. And at the top of the spectrum are very high-frequency, high-energy waves, like X-rays. Within the bonds between atoms, energy can be stored in another form.
Chemical.
During a chemical reaction, this energy can be released in other forms, like heat and light. Combustion is the rapid chemical reaction between a fuel and oxygen. In this case, the fuel is hydrogen. A firefly can convert chemical energy into light. Energy is a pattern that has to be recognized in what looks at first like a jumble of unrelated events. It was only after understanding how all these various energy forms are related to each other that we were able to see them in terms of their energy.
Energy, the single theme of life that weaves everything into common ground. What is the link between a firefly, the cry of a baby, a rocket heading high? They're all connected through the energy laws. For every action there's an energy cause. Energy.
The biggest stumbling block to our understanding of energy was a misunderstanding about heat. Until well into the 19th century, the prevailing scientific view was that heat was a form of matter, an invisible fluid called caloric that flowed into objects to make them hotter. It was a powerful theory because it explained many of the properties of heat. For example, the way matter expands when it is heated, which was attributed to caloric entering between its atoms and spreading them out. One of the key figures in debunking the caloric theory was the infamous Count Rumford. Born Benjamin Thompson in the British colony of Massachusetts, he soon developed an amazing knack for self-transformation. During the American Revolution, he worked as a British spy and used his natural scientific talents to write secret reports in invisible ink. After arousing suspicion, he fled to England, where he rose to high office and engaged in more double-dealing, spying for France, England's enemy. In the midst of all this intrigue, Rumford also carried on a brilliant scientific career. His most famous experiment took place in 1797. He noticed that when the barrel of a cannon was being bored out, an inexhaustible amount of heat was produced. Far more than could be accounted for by any caloric squeezed out of the metal. He put the entire apparatus underwater and astonished onlookers by bringing it to a boil. Where did all this heat come from? Rumford concluded it was from friction, and that heat was really a form of motion. In other words, heat was energy. In spite of Rumford, many scientists still hung on to the caloric theory. It was finally laid to rest by a man as modest as Rumford was arrogant, the English brewer and scientist James Joule. In the 1840s, Joule did a series of painstaking experiments to measure exactly what happens when work is transformed into heat. First, he measured the amount of work in foot-pounds it took to turn a spindle by attaching a weight to a string wrapped around it. Having calibrated the spindle, Joule could then turn it by hand, knowing exactly how much work he was doing with each turn. In this way, he measured the work needed to spin various devices that converted motion into heat. One was the newly invented electrical generator, which uses a wire coil revolving within a magnetic field to induce an electrical current. Joule surrounded the coil with a glass tube filled with a known amount of water at a known temperature. As he spun the tube, the electrical current heated the water. From the increase in temperature, Joule was able to calculate the amount of work it took to create 1 British thermal unit, or BTU. Joule then used the same technique to power a paddle wheel turning in water, the resistance of which converts the kinetic energy of the paddle wheel into heat. Again, Joule calculated the amount of work it took to produce 1 BTU. No matter what device he used, Joule's results were basically the same. He showed that the same amount of work produces the same amount of heat, no matter how it's done. This is known as the work-heat equivalence. Joule's work established the universal law that unites heat and all other energy forms, the first law of thermodynamics. It states that energy can be neither destroyed nor created, but only converted from one form to another. To honor his great scientific achievement, the primary unit of energy is named after Joule.
My father was the professor of physical chemistry at Manchester University, and sitting in my father's office, my father told me that Joule had come into that same office years before and explained his idea of the mechanical equivalence of heat, not to my father, but to some earlier professor of physical chemistry. And the professor had said to him rather disdainfully, well, if you're right, if I stir my tea, which is what the professor was in fact doing, the tea should get hotter, since the motion should be dissipated as heat. And with that he dismissed Joule with a laugh, and a year later Joule burst into his office and said, "It does!"
Even before Joule's great discovery, steam engines were providing a practical demonstration of it. They transform the chemical energy of coal or wood into the heat energy of steam, then into the kinetic energy of piston and wheel, which can be harnessed to do useful work. Steam engines vastly expanded our productive capacity. James Watt, the Scottish engineer who built the first modern steam engine in the 1770s, can also take credit for making the first energy measurements. For his unit of measure, he used the work capacity of a typical horse, or 1 horsepower. Watt was actually measuring power, which is related to energy, but different. Power is the rate at which energy is produced. That is the amount of energy produced per unit of time. The standard unit of power is named in honor of James Watt. 1 watt is equal to 1 joule per second. It takes 746 watts to equal 1 horsepower. The first law of thermodynamics is the fundamental principle of modern science. In 1905, Albert Einstein extended the first law to include the energy locked in the nucleus of an atom. Einstein calculated that the small amount of mass in a nucleus contains a huge amount of energy. His famous equation E equals mc squared equates this energy with mass times the square of the speed of light, a very large number. His prediction was later borne out with the discovery of the fission or splitting of the uranium nucleus, which led to the first atomic bomb. The bomb converts part of the nucleus into highly destructive heat and high-energy radiation. The same process, controlled form, turns water into steam in a nuclear power plant. The first law only tells us that when energy flows from one form to another, the total energy in the system stays the same. What it doesn't tell us is in which direction the energy is most likely to flow. That answer is found in another energy law, also dating back to the Victorian era. The second law of thermodynamics states that energy naturally flows from an organized to a disorganized state. Or in other words, the entropy or energy disorganization of the universe is ever increasing. There is an energy hierarchy, with the most highly organized and useful forms, those with the least entropy, at the top. At the bottom is energy in its most disorganized, useless form, with the most entropy. Energy naturally flows down this cascade of quality. For instance, the potential, then kinetic energy of a waterfall is highly organized and can be easily converted into electrical energy by spinning a turbine. However, a small amount of high-quality energy is dissipated into the useless energy of frictional heat, so entropy increases. This electrical energy can then be transmitted over long distances with a further leakage of waste heat, before being converted into another energy form, at which point the second law again takes its toll in entropy. An ordinary incandescent bulb reduces 95% of its electrical energy into waste heat. It is the second law that dictates that the age-old dream of a perpetual motion machine will forever remain just a dream.
Galileo, Newton, Watt, they were geniuses all. Without them we'd be freezing in the dark at the mall. James Joule found total energy remains the same.
No matter what its form.
That's why it carries his name.
Chemical, electrical, potential and heat. Radiant, kinetic, the list is incomplete. They're always changing back and forth, it's really quite a blur.
Oh, how could he?
I've forgotten nuclear.
Ride a barrel down the falls, then cook spaghetti with meatballs. Really make your friends amazed. Nuke it with some gamma rays. Fly to Venus in a rocket. Put your finger in a socket. You may suffer from exhaust, but none of that energy is ever really lost.
Then why can't we make a clean machine that moves perpetually? Cause there's another law with which all energy must agree. Whenever it changes form, it loses quality.
In other words,
damn that rising entropy.
It's entropy, you see, that turns finesse into mess. A palace to a pigsty, why it's simply scandalous. Energy once neat degenerates into waste heat.
We must repeat.
Because of entropy.
The second law of thermodynamics suggests that the Earth should have run out of useful energy long ago, that it should now be a desert, devoid of life. What has saved us is a constant infusion of new, high-quality energy from the sun. How does the sun get its energy in the first place? From unleashing the nuclear power of hydrogen. In the tremendous heat found in the sun's core, hydrogen nuclei fuse into helium in a process called thermonuclear fusion. It is similar to what happens during the explosion of a hydrogen bomb. As a result, some of the nuclear mass of the sun is converted into the radiant energy of sunlight. The Earth's atmosphere absorbs the sun's energy unevenly, which sets up the convection patterns of wind and water that drive our weather. These movements of moisture-laden air can carry tremendous amounts of energy, all of which can be traced back to the sun. A hurricane carries an energy equivalent 500,000 times greater than the first atomic bomb. But from the perspective of life on Earth, the most important role of the sun is to provide the chemical energy of food. It does this through an amazing energy conversion called photosynthesis. This takes place in the upper layer of green leaves, which contain a light-sensitive pigment called chlorophyll. Photosynthesis happens in two stages. In the initial light reaction, visible light from the sun strikes a chlorophyll molecule and kicks out an electron. This sets off a chain reaction of other electron transfers that builds up into an electrical charge. This electrical energy is finally discharged, splitting a water molecule into oxygen, protons, and electrons. The oxygen floats off into the air, and the remaining energy is converted into chemical form as an energy-storing molecule called ATP. ATP is the body's form of batteries and is how all living things temporarily store energy. The second stage of photosynthesis is called the dark reaction because it doesn't depend on sunlight. It converts the energy from the light reaction into food. But a new ingredient is required, carbon dioxide from the air. With an energy push from ATP, the carbon dioxide molecules combine with the protons and electrons from the light reaction to form glucose or sugar. In this plant lab at the University of Guelph, photosynthesis can be measured and studied under totally controlled conditions. The goal is to learn how to improve plant growth. All the ingredients of photosynthesis can be increased or decreased and the effect measured. When carbon dioxide is increased, within a few minutes, the rate of photosynthesis records an upward tick.
The sun sends rays traveling through outer space, photons of light that feed the human race. This solar thrill that turns on chlorophyll, the nourishing kiss of photosynthesis. To create this ecstasy, plants use this recipe. Add water to light, an electron takes flight, and oxygen is set free. The result is ATP. That's how plants store energy. Real cooking begins when CO2 comes in. It's a sugar factory. Ba-da-ba-ba-ba-da. Plants and trees are the base of a hierarchy. The rest of us too live off this chemistry. Yes, even beef starts off from a leaf. Life's secret is this: photosynthesis. Photosynthesis helps to clear carbon from the atmosphere. It takes CO2 in, releases oxygen. Photosynthesis helps to clear carbon from the atmosphere. It takes CO2 in, releases oxygen. Ba-da-ba.
Photosynthesis is actually only half the secret of life. The other half is how we and all other living things are able to extract and use that energy to keep alive. First, food is broken down in the mouth by chewing and by saliva, by muscle action in the esophagus, and by digestive chemicals in the stomach and duodenum. This reduces it back down to its component molecules, which are absorbed through the intestinal wall and enter the bloodstream. Sugar is the body's primary source of living energy. It enters the cell and is divided by enzymes into two smaller units. At the same time, some ATP is formed. These smaller molecules are then loaded into the mitochondria, the cell's power plants, where the rest of their fuel energy is extracted in a reaction with oxygen. First, they are broken down into energy-rich electrons and protons in a circle of reactions called the Krebs cycle. CO2 is released as a waste product, and a bit more ATP is produced. These electrons and protons are then passed along a chain of energy-transporting compounds, which convert most of their energy into ATP. The last link in this chain is oxygen, which absorbs the energy-drained electrons and protons to form water. What happens in the mitochondria is really a slow-motion version of combustion called respiration. Without oxygen, it would all come to a halt. Serious illness can affect the rate at which the body converts energy through respiration. Mark is 14 years old and about to undergo a liver transplant. This machine, by analyzing the amount of oxygen he breathes in and CO2 he breathes out, can measure how much food energy he is converting into ATP. This will give his doctors important information about his progress after the transplant. Photosynthesis and respiration together form the energy cycle of life. One process is the mirror image of the other as they transfer the same basic molecules back and forth. Photosynthesis uses CO2 and water and the energy of the sun to produce glucose along with oxygen. Respiration, on the other hand, starts off with glucose and oxygen and ends up with CO2 and water as it converts food energy into the living energy of ATP. The end products of one process are the building blocks of the other. Photosynthesis and respiration together create the engine that converts the energy of the sun into the energy of life.
Yes, your body is a power plant you're loading up each time you sup. The fuel you burn tastes better than crude oil, but it's all of a type, and it travels down a pipe. Down the hatch
Goes another batch.
no muss or fuss.
In the esophagus. Into the stomach where the next digestive facet is to mix it all together with hydrochloric acid.
And that's how we get our fuel. Turn something tasty into gruel. Break it down until it's just some molecules. From your gut, it goes into your bloodstream, down to a cell.
The truth we tell.
That's where it all converts into the energy of motion and heat.
How very neat.
Those calories
Become ATPs.
they come alive.
And give us drive. Transform by oxidation into work and perspiration. It's called respiration and it's food incineration.
What was photosynthesized, you may now have realized,
Takes the opposite path when it's metabolized. It's the circle of life that keeps us energized. No matter how it's obtained, it's never lost or gained. Energy, it's the pulse of life. It's what makes the world go round and round. Energy, it's the pulse of life. It's what makes the world go